Tonight we're going to take you somewhere no human being was ever meant to go. Not to a mountain peak, not to the bottom of the ocean, not to the frozen edges of Antarctica where the wind cuts like glass and the cold reaches inside your chest and squeezes. Tonight we're going somewhere far more hostile than any of those places, somewhere our bodies were never designed to enter, somewhere the universe itself seems to have decided that life, at least life like ours, simply does not belong. We're going to the edge of everything, to open space, and we're going to spend the next few hours understanding, quietly and honestly, exactly what would happen to you if you were there without protection. Not the Hollywood version, the real one, the one that is far stranger, far more intimate, and far more terrifying than anything a film has ever shown you. Here's what almost nobody tells you. We spend so much time dreaming about space. We name our children after astronauts. We build rockets and point them at the stars and call it the greatest achievement of our species. And it is. It genuinely is. But buried underneath all of that ambition, underneath all of that wonder and poetry and scientific triumph, is a truth that rarely gets mentioned in the speeches or the launch countdowns or the documentaries that show you the Earth from above with swelling music behind it. The truth is this: space is not waiting for us. Space is not indifferent to us. Space is actively, completely, and with absolute precision incompatible with everything that makes us alive. Your blood, your lungs, your bones, your eyes, your mind. Every single system inside you was built for one place and one place only, and the moment you leave that place unprotected, the universe begins taking you apart. Quietly, efficiently, without hesitation. By the end of tonight, you're going to understand exactly why the human body cannot survive a single day in open space. Not because of one dramatic catastrophe, but because of a dozen silent overlapping processes that begin within seconds of exposure and do not stop. You're going to understand what really happens in those first 10 seconds, what the vacuum actually does, and why it's nothing like you imagined, what radiation feels like from the inside, what happens to your blood, your bones, your vision, your sense of time and self when the Earth is no longer beneath your feet and the sky is no longer above your head. And somewhere in all of that, I think you're going to find something unexpected. Not just fear, but wonder. A deep, slow, almost overwhelming wonder at the fact that you are here at all. That the universe made something as fragile and as extraordinary as you. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Close your eyes for a moment. Just for a moment. I want you to imagine something very specific. You're standing outside. It is night. The air is cool against your skin, and you can feel it. That gentle pressure of the atmosphere against your face, your arms, your chest. You breathe in, and the oxygen moves through you like something ancient and automatic, the way it has moved through human beings for hundreds of thousands of years. Above you, the stars are out. Thousands of them, cold and white and impossibly far away. And somewhere up there, past the blue curve of the atmosphere, past the satellites, and the silence and the slowly spinning International Space Station, is the place we are going tonight. Open space. The real thing. And it is nothing like the stars make it look from down here. We have always looked up. That much I know about you, because you are here, in the quiet hours, listening to the universe being described in the dark. Human beings have been looking up at that sky for as long as we have existed. Long before we had words for what we were seeing, we were watching. The moon rising and falling, the slow wheel of constellations across the winter sky, the sudden white scratch of a meteor burning up in the upper atmosphere, gone before you could point at it. Something in us has always understood, on a level deeper than language, that there is more out there. That the sky is not a ceiling, that it is a door. And for most of human history, all we could do was stand at that door and look through it and wonder what was on the other side. Then, in the 20th century, we opened the door. On the 4th of October 1957, the Soviet Union launched Sputnik 1 into low Earth orbit, a metal sphere about the size of a beach ball beeping a simple radio signal back to the planet below. It was not much, but it was enough. It was the first time a human-made object had left the atmosphere and kept going. 4 years later, on the 12th of April 1961, a 27-year-old Soviet pilot named Yuri Gagarin became the first human being to leave Earth entirely. He was up there for 108 minutes, and when he came back, when the capsule burned through the atmosphere and he ejected and parachuted down to a field in Russia, the world changed. We had gone to space. We had actually gone. The door was open, and we had walked through it. And we have been walking through it ever since. 12 human beings walked on the surface of the moon between 1969 and 1972. Astronauts have lived and worked aboard space stations for months at a time. The International Space Station has been continuously inhabited since the 2nd of November, 2000. More than 2 decades of uninterrupted human presence in low Earth orbit. We have sent robotic probes to every planet in the solar system. We have landed on Mars. We have photographed the moons of Jupiter, the rings of Saturn, the icy plains of Pluto. We have pointed telescopes at the edge of the observable universe and seen light that left its source 13.4 billion years ago. We are extraordinary. There is no other word for it. And yet. Here is the thing most people do not realize. Even the people who follow every rocket launch and know every astronaut's name and have watched every documentary about the cosmos ever made, all of that, every single achievement, every orbit, every moonwalk, every spacewalk, every photograph from the edge of the solar system, was accomplished despite the fact that space is trying to kill us. Not metaphorically, not in the poetic sense that nature is indifferent and danger is always present, literally, physiologically. In specific, measurable, clinical ways that begin within seconds of unprotected exposure and do not stop until there is nothing left to stop. Space does not hate us. It is not dramatic about it. It simply operates according to physical laws that are entirely, completely, and without exception incompatible with human biology. That is what tonight is about. Not the romance of space, though the romance is real, and I want you to hold on to it. Not the achievement of space exploration, though that achievement is genuine and it deserves every word of praise it has ever received. Tonight is about something quieter and stranger and, I think, more interesting than either of those things. Tonight is about the gap between what we dream space is and what space actually is, the gap between the astronaut waving from the rocket and the biological reality of what that astronaut's body is enduring every single moment they are up there, the gap between the stars as they look from your backyard on a clear night and the stars as they actually exist, surrounded by distances so vast and conditions so extreme that a human being transported there without protection would not last long enough to register what they were seeing. We are going to close that gap tonight, slowly and gently and without rushing. We are going to talk about what a vacuum actually is and what it does to soft tissue and blood and the delicate pressure systems that keep your body in one piece. We are going to talk about temperature, not the cold you know, but a cold so absolute it exists at the very bottom of the thermometer, at the place where molecular motion almost stops entirely. We are going to talk about radiation raining down from dying stars, passing through spacecraft walls and human flesh as though neither one exists. We are going to talk about what happens to your blood when gravity disappears, and what happens to your bones when there is nothing pushing back against them, and what happens to your mind when the only thing outside the window is infinite black silence in every direction for as far as the universe extends. And here is what I want you to hold on to as we go. This is not a frightening story, even though some of what I am going to tell you is genuinely terrifying. This is a story about you, about the body you are lying in right now, this extraordinary and improbable machine that breathes without being asked to breathe and circulates blood without being asked to circulate it, and maintains a temperature of 37 degrees Celsius in a world that is constantly trying to pull that temperature away from it. Your body is the product of 3.8 billion years of evolution. Every system inside you is the answer to a problem that life spent billions of years solving. And tonight, I want you to understand exactly how precisely those solutions were calibrated, by seeing what happens when you take them away. Space is the mirror that shows us what Earth really is, and what we really are. Let that thought settle over you like a blanket as we begin. There is something around you right now that you have never once thought to be grateful for. You cannot see it. You cannot taste it. Not really, not the way you taste food or water. You cannot hold it in your hand or point to it and say, "There, that is the thing that is keeping me alive." And yet without it, you would be dead in minutes, probably less. It surrounds you completely, from the moment you are born to the moment you die, pressing gently against every centimetre of your skin with a force of about 14.7 pounds per square inch. It has been there your entire life, so constant and so invisible that your brain has simply stopped registering it the way it stops registering the sound of a fan running in a room you have been sitting in for an hour. You have tuned it out entirely. That thing is Earth's atmosphere, and tonight, before we can talk about what space does to your body, we need to talk about what the atmosphere does for it. Because the atmosphere is not just air. It is the most sophisticated life support system in the known universe, and it has been running without interruption for about 4 billion years. Let me give you a sense of the scale of what we're talking about. The atmosphere extends roughly 10,000 kilometers above the surface of the Earth, though the vast majority of its mass is concentrated in the lowest layer, the troposphere, which reaches only about 12 kilometers up. 12 kilometers. That sounds like a lot until you consider that the Earth itself has a radius of about 6,370 kilometers. If you were to shrink the Earth down to the size of a standard classroom globe, the kind that sits on a teacher's desk, the atmosphere would be roughly the thickness of a coat of paint on the surface of that globe. A single coat of paint. That is the bubble that stands between you and the void. That is the margin by which you exist. And inside that thin, improbable layer of gas, something remarkable is happening at all times. The atmosphere is not simply a container of oxygen that you breathe in and out. It is a dynamic, constantly moving, constantly self-regulating system that does several things simultaneously, all of them essential to your survival. It filters out the vast majority of the solar radiation that streams toward Earth from the sun, radiation that would otherwise burn through your DNA like fire through paper. It distributes heat from the equator toward the poles, preventing the kind of extreme temperature swings that would make most of the planet uninhabitable. It carries water vapor around the globe and releases it as rain, feeding every river and aquifer and cell in every living thing on the surface. And it maintains a pressure, that steady, gentle, invisible push against your skin, that is absolutely critical to the function of every fluid system in your body, from your blood to the fluid in your eyes to the gas dissolved in your tissues. Here is the thing most people do not realize about pressure. We tend to think of pressure as something that crushes, as something dangerous, and in extreme forms it is. But the pressure your body exists under at sea level is not crushing you. It is holding you together. Think of your blood as a liquid that wants to behave like a liquid, staying fluid and flowing and carrying oxygen to your cells the way it is supposed to. That behavior, the behavior of staying liquid, depends on the pressure around it being high enough to prevent it from doing something else instead. From vaporizing, from boiling. Not because of heat, but because of the absence of pressure. Water boils at 100 degrees Celsius at sea level. But if you reduce the pressure enough, water will boil at room temperature, at body temperature. Which means that in a low-pressure environment, say the near-perfect vacuum of open space, the fluids in your body would begin to change state. Not dramatically, not explosively, but they would begin. And that is a process your body was never designed to survive. The atmosphere also does something that we are almost philosophically incapable of appreciating from the inside, which is that it makes the surface of this planet thermally habitable in a way that is extraordinarily rare in the universe. The average temperature on the surface of the Moon, which has no atmosphere, swings from about 127 degrees Celsius in direct sunlight to negative 173 degrees Celsius in the shade. That swing happens not over seasons or even days as we experience them, but over the course of a single lunar day. The same rock, in the same location, experiencing a 300-degree temperature shift depending on whether the sun is hitting it or not. Earth's atmosphere absorbs and redistributes solar energy in a way that keeps our surface temperatures within a range that liquid water can exist, that cells can function, that proteins do not unravel, and enzymes do not freeze solid. It is a thermal buffer of almost incomprehensible sophistication, and it operates entirely passively, without any intervention or maintenance required from us. Now think about what it means to leave it. Not the drama of the rocket launch, though that drama is real. Not the technical achievement of escaping Earth's gravity well, though that achievement is staggering. Think instead about the quiet biological fact of what crossing that boundary represents. You're a system, a beautifully calibrated, enormously complex biological system, that was built from the cellular level up, to operate inside the bubble. Every enzyme in your body has an optimal temperature range derived from the surface conditions the bubble maintains. Every cell membrane in your body has a structural integrity calibrated to the pressure the bubble exerts. Every breath you take is premised on the assumption that the gas mixture the bubble contains, roughly 78% nitrogen, 21% oxygen, and trace amounts of other gases, will be available to you. Remove the bubble, and you do not simply lose the air. You lose the entire operating environment that life on Earth spent billions of years engineering itself to require. When astronauts leave Earth aboard a spacecraft, they carry a piece of the bubble with them. The cabin of the International Space Station is pressurized to roughly the same atmospheric pressure as sea level. The air inside is carefully maintained at an oxygen and nitrogen mixture, similar to what you are breathing right now. The temperature is regulated. In other words, the spacecraft is a bubble inside the bubble, a small engineered replica of the conditions at Earth's surface, carried into a place where those conditions are catastrophically absent. And when an astronaut performs a spacewalk stepping outside the station into open space, they climb into a spacesuit that is, itself, a bubble. A wearable atmosphere, a miniature Earth wrapped around a single human body. Because without it, the moment they stepped outside, the universe would begin undoing 3.8 billion years of evolutionary work. Quietly, systematically, without hesitation. The bubble is everything. And tonight we are going to find out exactly what happens when it is gone. Let me ask you something. When you imagine what it would feel like to be exposed to open space without a suit, what do you see? If you have watched science fiction films, and most of us have, you probably have a very specific image in your mind. Maybe it is instantaneous freezing, the body locking up in a crystalline sculpture of ice in a fraction of a second. Maybe it is explosion, the internal pressure of the body overwhelming the external vacuum and the whole thing simply coming apart in a cloud of red mist. Maybe it is something slower but equally dramatic, the eyes bulging, the face contorting, the kind of theatrical death that fills 3 seconds of screen time and makes the audience gasp. I want you to gently set all of that aside tonight, because the reality of what actually happens to an unprotected human body in the first 10 seconds of exposure to open space is something that no film has ever quite captured, and in some ways, the truth is more unsettling than any of the fictions, not because it is more violent, but because it is so much more intimate. The first thing to understand is what you are actually being exposed to. Open space is not filled with something deadly, the way a room filled with toxic gas is filled with something deadly. It is not an aggressive substance that attacks you. It is the absence of something, the near total absence of pressure, of gas molecules, of the atmospheric medium your body has always assumed would be there. In the vacuum of space, the pressure drops to essentially zero, and your body, which has spent your entire life operating under the assumption that there would be 14.7 pounds of pressure per square inch, pushing back against it from every direction, suddenly has nothing pushing back at all. The differential between the pressure inside you and the pressure outside you becomes enormous, and your body, being a physical object subject to physical laws, begins to respond to that differential immediately. In the first second, you would feel it in your skin. Not pain exactly, not at first. More like a sudden, total change in the sensation of your own body surface as the pressure differential causes your tissues to begin expanding slightly outward. Your skin would feel strange, taut in a way it has never felt before, like something underneath it is pushing against it from the inside. In the same first second, if your mouth was closed and you tried to hold your breath, which would be a natural instinct and also exactly the wrong thing to do, the expanding gases in your lungs would have nowhere to go. The gas in your lungs is at body pressure. The space outside your body is at zero pressure. Hold your breath in a vacuum and your lungs will rupture within seconds. The correct action, counterintuitive as it sounds, is to exhale, to open your mouth and let the air out. Astronauts are trained on this. The body's instinct is to hold on. The physics demand that you let go. By the 3rd or 4th second, something would happen that is both strange and deeply specific. The moisture on the surface of your eyes and on your tongue would begin to vaporize. Not because it is hot. The temperature of the space environment in those first seconds would be largely irrelevant. The thermal transfer between your body and the vacuum would actually be quite slow, because a vacuum has no medium through which to conduct heat away from you quickly. But vaporization does not require heat when pressure is low enough. At near zero pressure, water boils at body temperature, so the thin film of moisture on your eyes would bubble gently, and your tongue would feel the same strange fizzing sensation, like the faintest carbonation, as the water on its surface changed state. It would not be painful, at least not yet. It would be profoundly disorienting. Your vision would blur immediately as the tear film on your eyes disrupted. The world, or whatever was in front of you, would go soft and indistinct within a few seconds of exposure. Between 5 and 8 seconds you would lose consciousness, not from the cold, not from any dramatic physical trauma, but from hypoxia, the deprivation of oxygen to the brain. Here is what happens. In a vacuum, the oxygen dissolved in your blood begins to come out of solution rapidly, the same way carbon dioxide comes bubbling out of a soda when you release the pressure by opening the cap. Your blood, suddenly without the atmospheric pressure that kept gases dissolved within it, begins to off-gas. The oxygen your red blood cells were carrying begins to escape the tissues, and your brain, which consumes roughly 20% of your body's oxygen supply, despite being only about 2% of your body weight, detects the shortage almost instantly. The brain is extraordinarily sensitive to oxygen deprivation. You would begin to feel the first effects of hypoxia, a strange lightness, a narrowing of awareness, a dreamlike quality to whatever your blurring vision was still registering, within about 15 seconds of oxygen loss. At 5 to 8 seconds of total vacuum exposure, unconsciousness would follow, quietly, almost gently, like a light being turned off in a room you were just standing in. And here is what would not happen, because I think this matters as much as what would. You would not explode. The human body is not a pressurized container in the way that a sealed metal tank is a pressurized container. Your skin is elastic and resilient, and while it would swell, astronauts who have experienced accidental partial vacuum exposure in test environments reported their suits inflating around them and their skin swelling where it was exposed. It would not rupture. You would not freeze instantly. The vacuum is an extraordinarily poor conductor of heat, and the thermal radiation from your body into space would take many minutes, not seconds, to significantly lower your core temperature. Your blood would not boil in the Hollywood sense of boiling, a roiling, explosive internal eruption. The vaporization process would be more subtle than that, more systemic, more quiet. The body in space does not go out with a bang. It goes out with a strange, expanding, oxygen-starved silence. In 1965, a NASA technician named Jim LeBlanc was accidentally exposed to near-vacuum conditions in a test chamber at the Johnson Space Center when his pressure suit developed a leak. The suit depressurized in seconds. LeBlanc reported feeling the saliva on his tongue beginning to boil before he lost consciousness. He was unconscious within 14 seconds. The chamber was repressurized quickly, and he survived without permanent injury. It is one of the only documented cases of a human being experiencing near-vacuum exposure and living to describe it. And what he described was not the chaos of science fiction. It was quiet, it was fast, and it was intimate in a way that is difficult to articulate. The body turning against itself not through violence, but through the simple, merciless logic of physics operating without the protection of the bubble. 10 seconds, that is the margin. 10 seconds between the person you are right now and the silence of space. Hold that thought as we go deeper into what comes next. There is a word that gets used a lot in discussions about space, and I want to spend some time with it tonight because I do not think we ever really let it land. The word is vacuum. We use it casually. We use it for the machine that cleans our floors, which creates a small and entirely manageable pressure differential to suck up dust. We use it as a synonym for emptiness, for absence, for the general idea of nothing being there. But the vacuum of space is not a mild version of these things. It is not a stronger version of the vacuum cleaner, or a more complete version of the emptiness in a room with the furniture removed. The vacuum of space is something categorically different from any experience of absence your senses have ever registered. And understanding what it truly is, not as a metaphor, not as a poetic image, but as a physical reality, is essential to understanding why your body cannot exist inside it. A vacuum, in the strictest scientific sense, is a region of space from which matter has been removed. A perfect vacuum would contain absolutely no particles at all. No gas molecules, no dust, no photons, nothing. In practice, a perfect vacuum does not exist anywhere in the universe, including in deep space, where there is always at least a scattering of hydrogen atoms and the faint background radiation left over from the Big Bang. But the vacuum of interplanetary space is close enough to perfect that the distinction barely matters for the purposes of your biology. The pressure in interplanetary space is roughly 10 to the negative 10 pascals. To give you a sense of what that means in terms you can feel, the atmospheric pressure at sea level on Earth is about 101,000 pascals. The pressure in the best laboratory vacuums humans have ever created on Earth is around 10 to the negative 11 pascals. Open space is, by every practical measure, as empty of pressure as anything in the known universe. And your body, remember, is pressurized. It is a system of fluids and gases and soft tissues operating under the continuous assumption that something is pushing back. The condition that results from placing a pressurized biological system into a near-perfect vacuum has a clinical name. It is called ebulism. The word comes from the Latin ebulliere, meaning to bubble up or to boil over, and that name is precise, because what ebulism describes is exactly that. The formation of bubbles in the body's fluids caused not by heat, but by the sudden and catastrophic loss of ambient pressure. Think of a sealed bottle of carbonated water. The carbon dioxide dissolved in that water stays dissolved because of the pressure inside the bottle, which keeps the gas in solution. The moment you open the bottle, the moment you release that pressure, the gas comes out of solution, and you see it immediately as bubbles rising to the surface. That is, in a simplified but structurally accurate way, what begins to happen to the fluids in your body when you are exposed to the vacuum of space. The dissolved gases in your blood and tissues, gases that were perfectly stable under Earth's atmospheric pressure, suddenly have no pressure keeping them in solution. They begin to come out, they begin to bubble. The first fluids affected are those closest to the surface and those with the lowest threshold for vaporization. The moisture on your eyes and tongue, as we discussed, begins to vaporize almost immediately. But ebulism goes deeper than the surface. Within seconds of pressure loss, the venous blood returning to your heart begins to show bubble formation. The synovial fluid in your joints, the lubricating fluid that allows your knees and elbows and shoulders to move smoothly, begins to vaporize, causing your joints to swell and stiffen painfully. The soft tissues of your body begin to swell as the interstitial fluid within them transitions toward a gaseous state. Eyewitness reports from the Jim LeBlanc incident, which we touched on in the previous chapter, included observers watching his hand swell visibly inside his partially pressurized suit within seconds of the pressure loss. The swelling is not damage in the way a bruise is damage. It is the body literally inflating from the inside as its fluids change phase. Here is the thing most people do not realize about ebulism. It does not kill you quickly through any single dramatic mechanism. It kills you, or would kill you, in a full vacuum exposure, through accumulation. Through the compounding of dozens of small physiological crises happening simultaneously. The joint swelling impairs movement. The vascular bubble formation impairs circulation. The off-gassing of oxygen from the blood impairs cellular respiration. The loss of moisture from mucosal surfaces impairs respiratory function. None of these things alone would necessarily be fatal within the first minute. All of them together, operating simultaneously in a body that has already lost consciousness from hypoxia within the first 15 seconds, create a cascade of physiological failure that, without repressurization, would be irreversible within about 90 seconds to 2 minutes. The vacuum does not strike like a weapon. It dismantles like a process. I want to give you an analogy that I think captures something true about this. Imagine a complex piece of machinery, something intricate and finely tuned, like a mechanical watch. Every gear and spring inside it is calibrated to operate within a specific range of conditions. Temperature, humidity, pressure, all of it within narrow tolerances. Now imagine placing that watch in an environment where all of those conditions are simultaneously removed or inverted. The watch does not explode. It does not catch fire. It simply begins to fail, component by component, each failure affecting the next, the whole system degrading in a cascade of small malfunctions until nothing is working anymore. Your body in a vacuum is that watch. The vacuum is not aggressive. It does not attack. It simply removes the conditions under which the machinery was designed to function, and then waits while the machinery undoes itself. And yet, and I want you to hold on to this. Ebulism is survivable, within limits. The Jim LeBlanc incident demonstrated this. Laboratory animals exposed to vacuum conditions for up to 90 seconds have been successfully resuscitated with full neurological recovery. The key variable is time, and the key intervention is repressurization. The moment atmospheric pressure is restored, the bubbles in the blood begin to reabsorb, the vaporized fluids begin to recondense, the swelling begins to subside. The body, given the chance, begins to undo what the vacuum did to it, because the body is not broken by brief vacuum exposure. It is temporarily operating outside the conditions it requires. Restore those conditions quickly enough, and it remembers what it was supposed to be doing. The vacuum has no mercy, but it also has no malice. It simply is what it is, and what it is, for any unprotected human being, is the most complete and efficient negation of the conditions necessary for life that the universe has yet produced. Somewhere in that fact, if you sit with it long enough, there is a kind of terrifying clarity. The universe is not hostile to us. It is simply indifferent in a way that feels, from the inside, exactly like hostility. When people imagine space, they imagine cold. And they are right to imagine cold, because space is extraordinarily, almost incomprehensibly cold. But the cold of space is not the cold you know. It is not the cold of a January morning when the wind comes off the water and your breath fogs in front of your face and your fingers go numb inside your gloves after 10 minutes. It is not even the cold of Antarctica, where temperatures can drop to negative 89 degrees Celsius and exposed skin can suffer frostbite in under a minute. The cold of space is something that exists in a different category from all of those things, something that requires a different kind of thermometer to measure and a different kind of imagination to grasp. And the truly strange thing, the thing that makes the thermal environment of space so much more complex and dangerous than simply saying it is cold, is that space is not uniformly cold at all. In some ways, space is also extraordinarily lethally hot. Both things are true simultaneously, and understanding how that is possible is one of the keys to understanding why the human body is so completely unsuited to survive there. Let us start with the cold, because the cold is the part that reaches deepest. The baseline temperature of open space, the temperature of the cosmic microwave background radiation that fills the universe in every direction, the faint thermal echo of the Big Bang itself, is approximately 2.7 Kelvin. To translate that into more familiar terms, that is negative 270.4 degrees Celsius or negative 454.8 degrees Fahrenheit. Absolute zero, the theoretical point at which all molecular motion stops completely and nothing can be any colder, is 0 Kelvin. 2.7 Kelvin is just barely above that floor. It is not a temperature that exists anywhere on the surface of Earth under any natural conditions. It is not a temperature that any living thing has ever experienced and survived. It is the cold at the bottom of the universe, the cold that has been soaking into everything since the first light of creation faded and the darkness settled in, and it has been there for 13.8 billion years. But here is the thing most people do not realize about thermal physics in a vacuum, and it is the detail that makes the temperature of space so much stranger than the simple number suggests. Temperature, as you experience it, is largely a function of conduction and convection, heat moving from one object to another through direct contact, or through the movement of a medium like air or water. When you step outside on a cold day and the wind cuts through your jacket, what you're feeling is convective heat loss, the air moving across your skin and carrying your body heat away with it. When you press your hand against a cold metal railing and it feels immediately colder than a wooden railing at the same temperature, what you're experiencing is conductive heat loss. The metal drawing heat away from your skin faster because it is a better conductor. Both of these processes require a medium. They require something to move the heat from your body to the environment. In a vacuum, there is no medium. There is no air to convect your heat away. There is no surface conducting it out of you. The only mechanism by which your body can lose or gain heat in a vacuum is radiation, the emission and absorption of electromagnetic energy, and radiation is slow. Compared to conduction and convection, radiation is a remarkably inefficient way to exchange heat, which means that in the vacuum of open space, your body would not freeze in seconds the way science fiction suggests. If you were suddenly transported into open space far from any star, your body would begin to radiate its heat away into the cosmic background, but that process would take many minutes, perhaps longer than 30 minutes, to significantly lower your core temperature, You would lose consciousness from hypoxia and be killed by embolism long before you froze. The cold of deep space, as absolute as it is almost irrelevant to the immediate timeline of vacuum exposure because the vacuum itself prevents the rapid heat transfer that would make cold an acute danger. In a terrible and paradoxical way, the very thing that makes space so cold, the absence of any medium, is also what prevents that cold from reaching you quickly. But that is only half of the thermal story. The other half involves something most people never think about when they imagine space: sunlight. In Earth's orbit, and throughout the inner solar system, the sun is an extraordinarily powerful source of radiant energy. At the distance of Earth's orbit, the sun delivers roughly 1,360 watts of energy per square meter of surface facing it. That energy arrives as electromagnetic radiation across a spectrum from ultraviolet through visible light to infrared. On Earth, the atmosphere absorbs a significant portion of this energy before it reaches the surface, and the planet's thermal mass and air circulation spread whatever remains across the globe. But in space, there is no atmosphere to absorb it, no air to spread it, no thermal mass to buffer it. A surface facing the sun in low Earth orbit absorbs that full 1,360 watts per square meter, with nothing to moderate it. The result is a thermal environment of violent extremes. Surfaces in direct sunlight in low Earth orbit can reach temperatures of around 120 degrees Celsius, well above the boiling point of water. The same surface, rotated into shadow, can plunge to negative 150 or even negative 170 degrees Celsius in minutes. The International Space Station in its orbit passes through roughly 16 sunrises and 16 sunsets every single day, cycling through this extreme thermal range constantly. The station's exterior is covered in specialized multi-layer insulating blankets and thermal control systems specifically designed to manage this environment. Without them, the temperature swings would crack and warp the structure within hours, and for an unprotected human body, the implications are stark in both directions. In sunlight, exposed skin would begin to burn from radiant heating, and intense ultraviolet exposure almost immediately. In shadow, the slow radiation of body heat into the cosmic cold would eventually inexorably lower your core temperature toward a range incompatible with cellular function. Your body has a thermal regulation system that is, under normal Earth conditions, remarkably effective. Your hypothalamus monitors your core temperature continuously and deploys an arsenal of responses to keep it within a narrow range of roughly 36 to 37.5 degrees Celsius. Sweating, shivering, vasodilation, and vasoconstriction. The rerouting of blood flow to prioritize core organs when the periphery gets cold. These are elegant, finely tuned mechanisms built by billions of years of evolution to handle the thermal challenges of life on Earth. But they were built for an environment where heat transfer happens through air and water and physical contact. They were not built for a vacuum. They were not built for a place where the sun can heat one side of your body to over 100 degrees, while the other side slowly radiates its warmth into a darkness that is barely above absolute zero. Space does not just challenge your thermal regulation system, it renders it irrelevant. And in the quiet of tonight, as you lie warm and pressurized and perfectly buffered from all of that by the thin coat of paint that is our atmosphere, I think that is worth sitting with for a moment. Right now, without you asking it to, without you thinking about it even for a fraction of a second, your body is doing something it has been doing every moment of your life since the first breath you ever drew. It is pulling oxygen out of the air around you, binding it to hemoglobin molecules in your red blood cells, and carrying it through roughly 97,000 kilometers of blood vessels to every cell in your body. 97,000 kilometers. If you stretched your circulatory system out in a single line, it would wrap around the Earth more than twice. And along every centimeter of that extraordinary network, the same transaction is happening continuously. Oxygen delivered, carbon dioxide collected, cell by cell, moment by moment, the fundamental metabolic exchange that defines the difference between being alive and not being alive. You do not notice it. You have never noticed it. It runs in the background of your existence like the operating system of a computer, invisible and automatic and absolutely non-negotiable. Stop it for long enough, and everything else stops too. The relationship between oxygen and the human body goes back approximately 2.4 billion years to an event scientists call the Great Oxidation Event. Before that moment, Earth's atmosphere contained almost no free oxygen. Life existed, but it was anaerobic life, bacteria and microorganisms that had no use for oxygen and in fact found it toxic. Then photosynthetic cyanobacteria began releasing oxygen as a byproduct of converting sunlight into energy, and over hundreds of millions of years that oxygen accumulated in the atmosphere until it reached concentrations lethal to the anaerobic organisms that had dominated the planet. It was, in a very real sense, the first mass extinction caused by atmospheric change. But from the catastrophe of that ancient die-off emerged the lineage that would eventually produce you. We are the descendants of life that did not merely tolerate oxygen, but rebuilt its entire energy metabolism around it, making that one molecule so central to every cellular process that we cannot go more than a few minutes without it before the most complex and essential structure in our body begins to die. That structure is your brain. And the timeline of what happens to it when oxygen is removed is both precise and, once you know it, impossible to unknow. In the first 15 seconds of complete oxygen deprivation, the oxygen already dissolved in your blood and present in your lungs is rapidly consumed by your body's tissues. The brain, which accounts for roughly 2% of body weight, but demands approximately 20% of the body's total oxygen supply, begins registering the shortage almost immediately. In those first 15 seconds, you might feel a strange lightness, a loosening of thought, a dreamlike softening of the edges of perception, as though the world were becoming less solid and more impressionistic. People who have experienced hypoxia in controlled research environments often describe it as not unpleasant, which is one of the most unsettling things about it. The brain, as it begins to fail, does not reliably signal its own failure through pain or alarm. It signals it through a dissolving warmth that feels, in the moment, almost like drifting towards sleep. Between 15 and 20 seconds of complete oxygen loss, consciousness ends. Not with a dramatic collapse or visible convulsion in those earliest moments, but with a simple and total dimming of awareness, a narrowing of the field of experience to a single point, and then nothing. Aerospace researchers have measured this window carefully through controlled hypoxia studies, where subjects breathe nitrogen instead of air, while researchers monitor the precise moment cognitive function degrades and awareness fails. The results are consistent and sobering across decades of research. 15 seconds is the window. In a full vacuum exposure, where the body is simultaneously managing pressure loss, ebulism, and the off-gassing of dissolved blood oxygen, that window may be shorter still because the oxygen crisis does not arrive alone. It arrives as part of a cascade, and the brain, overwhelmed on multiple fronts at once, goes dark faster than any single threat would cause it to. But the oxygen clock does not stop counting when consciousness ends. This is the part that I find most quietly terrifying, and I want you to stay with it for a moment even as you let yourself relax into the dark. The brain is not a uniform structure. Different regions carry different metabolic demands and different tolerances for deprivation. The brainstem, which governs the most fundamental automatic functions, the heartbeat, the reflex arc, the basic maintenance of the body as a biological machine, is relatively more tolerant of oxygen loss than the cerebral cortex. The cortex, which is the seat of your thoughts, your memories, your language, your sense of humor, your grief, your recognition of faces you love, the specific and irreplaceable texture of being you, is the most oxygen-hungry structure in the most oxygen-hungry organ in your body. It is also the most vulnerable. It begins to suffer irreversible damage within 4 to 6 minutes of complete oxygen deprivation, even after consciousness has long since gone, which means there is a window, narrow and terrible, in which the part of you that pumps blood is still running, but the part of you that makes you you is already being quietly erased. Physicians call this anoxic brain injury, and they measure its progression in minutes with the kind of clinical precision that comes from decades of observing it in drowning victims and cardiac arrest patients. 4 to 6 minutes for the onset of irreversible cortical damage, 8 to 10 minutes before the damage becomes catastrophic and widespread. Resuscitation within those early windows can preserve function. Beyond them, even if the heart is restarted and breathing is restored, what remains may be a body that no longer contains the person who inhabited it. The oxygen clock is not simply a countdown to unconsciousness. It is a countdown to the dissolution of self, and it runs from the moment the atmosphere disappears, silently and without pause, regardless of whether the person experiencing it is aware it has started. I want you to translate that into the context of space, and specifically into the context of everything we've been building across these chapters. In an unprotected vacuum exposure, you lose consciousness within 15 to 20 seconds. That is the acute timeline. But the deeper question, the one that haunts the margins of every discussion of human space survival, is not simply whether the body can be kept alive, it is whether the person can be kept intact. The oxygen clock places a boundary around something far more precious than biological function. It places a boundary around continuity of self, around the specific, accumulated, utterly singular version of awareness that is you, reading these words in the dark, breathing without thinking about breathing, trusting without needing to think about it that the air will be there the next time your lungs reach for it. Space removes that trust. Space removes the ground beneath the trust. And in removing it, it reveals something extraordinary about what that trust is built on. Not on anything permanent, not on anything guaranteed, but on the thin, ancient, almost miraculous fact of an atmosphere that has been doing its job quietly and continuously for 4 billion years. Take a slow breath right now. Feel it move through you. That breath is the clock that never stops. And in the silence of space, there is nothing left to wind it. There is something falling on you right now. It has been falling on you your entire life, and you have never felt it, never seen it, never had any sensory experience of it whatsoever. It passes through the walls of the room you're in. It passes through the roof above you and the floor beneath you. It passes through your skin and your muscle and your organs without slowing down, without asking permission, without leaving any trace you could detect with your unaided senses. It is radiation in its various forms, and the reason you are not being harmed by it right now is not because it is absent. It is because you are sitting inside a protection system of almost incomprehensible sophistication. Earth's magnetic field, a vast and invisible bubble of electromagnetic force generated by the churning molten iron at the planet's core, deflects the most dangerous high-energy particles away from the surface before they can reach you. The atmosphere absorbs much of what gets through, and the combination of the two has been running continuously, reliably, without interruption, for billions of years. In space, beyond the protection of that system, the radiation environment is something that no analogy drawn from everyday life can quite prepare you for. Let me give you a map of what that environment actually contains, because it is not a single thing. It is a layered, overlapping collection of different radiation sources, each with its own character and its own specific way of interacting with biological tissue. The first and most familiar source is the Sun. Our star continuously emits a stream of charged particles, mostly protons and electrons, called the solar wind. Under normal conditions, the solar wind is relatively low energy and is handled efficiently by Earth's magnetic field, which funnels the particles toward the poles where they produce the aurora borealis and the aurora australis, those luminous curtains of light that appear in the high-latitude night sky. But the Sun also periodically produces violent eruptions called solar particle events, or solar flares and coronal mass ejections, which can release enormous bursts of high-energy protons in a matter of hours. The radiation dose from a major solar particle event for an unprotected astronaut in deep space could be lethal within hours. This is not a theoretical risk. It is a planned-for contingency on every deep space mission, and it is one of the reasons the International Space Station has designated shelter areas with additional radiation shielding. The second source is more exotic and, in some ways, more terrifying precisely because it is so constant and so inescapable. Galactic cosmic rays are high-energy particles, primarily protons and atomic nuclei, that originate outside our solar system. They come from supernovae, the violent deaths of massive stars, from neutron stars, from the jets of active galactic nuclei, from sources so distant and so energetic that the particles they produce travel for millions or billions of years before arriving at our little corner of the galaxy. By the time they reach us, they are moving at a significant fraction of the speed of light, carrying energy so high that no spacecraft wall currently in existence can stop them. The shielding that protects astronauts from most forms of radiation is largely ineffective against the most energetic galactic cosmic rays. They pass through aluminum walls, through water tanks used as radiation barriers, through the body itself, as though none of it is there. And as they pass through biological tissue, they leave a trail of ionization in their wake, breaking chemical bonds, damaging DNA, disrupting the molecular machinery of cells in ways that accumulate over time. Here is the thing most people do not realize about radiation damage in the context of space travel. It is not primarily an acute hazard the way a massive solar particle event would be. For astronauts on the International Space Station, which orbits within the partial protection of Earth's magnetic field at an altitude of roughly 400 kilometers, the radiation dose is manageable, approximately equivalent to 10 chest X-rays per year, or roughly the same annual dose as a frequent long-haul airline pilot receives. Elevated compared to sea level, certainly, but within ranges that medicine has studied and can monitor. The problem deepens dramatically the moment you leave low Earth orbit. Beyond the magnetic field's protection, in the interplanetary space between Earth and Mars, the galactic cosmic ray dose increases by a factor of roughly 100 compared to the surface. A 6-month transit to Mars would expose an astronaut to a radiation dose that significantly exceeds the lifetime career limits set by space agencies for their astronauts. And there is currently no lightweight practical shielding material that can stop galactic cosmic rays without adding so much mass to a spacecraft that launching it becomes economically and technically impossible. But there is one aspect of space radiation that I keep coming back to, because it is so strange and so intimate that it crosses from science into something that feels almost like poetry, though dark poetry. Astronauts who close their eyes in the darkness of space, particularly when passing through regions of higher radiation intensity, sometimes see flashes of light. Not from any external source, not from equipment or instrumentation, from inside their own visual cortex. These flashes, which astronauts have reported since the Apollo missions in the late 1960s and early 1970s, are caused by cosmic ray particles passing directly through the eye and the brain, and triggering neurons in the visual pathway as they go. The particles are moving too fast and carrying too much energy to be stopped by the skull or the eye socket or the retina. They simply pass through all of it and fire whatever they happen to touch on the way. What the astronaut sees is the ghost of a particle that was born in the death of a star, possibly millions of light years away, that has been travelling through space for longer than our sun has existed, and that has chosen, in its final moments of interaction with matter, to pass through a human brain and leave a tiny, inexplicable flash of light behind it. I find that almost unbearably beautiful and terrifying in equal measure. The idea that we are permeable to the universe in that way, that the deaths of ancient stars can reach inside our heads and touch our neurons, that we are not sealed off from the cosmos, not even inside our own skulls. The atmosphere and the magnetic field give us the comfortable illusion of being separate from space, of being in here while the universe is out there. But the cosmic rays disagree. They have always disagreed. They fall through us every day, even here on the surface, even in this room, even right now as you lie still and breathe slowly in the dark. The atmosphere stops most of them. The magnetic field deflects most of them, but some always get through. Some always have. And in space, without those defences, the rain does not become a drizzle. It becomes a flood. A quiet, invisible, relentless flood that your body was never built to stand in for long. The universe is always reaching in. Down here, we're just barely managing to keep the door closed. Gravity is so constant, so omnipresent, so woven into every moment of your physical existence, that your body has stopped treating it as a variable. It treats it as a fact, a given, the flaw of reality itself. Every system inside you, from the way your heart pumps to the way your kidneys filter, to the way fluid distributes itself through your tissues, was calibrated over millions of years of evolution to operate in a world where 9.8 meters per second squared of gravitational acceleration is always pulling everything downward. Your cardiovascular system, in particular, is a masterpiece of engineering specifically adapted to this fact. Your heart pumps harder to push blood upward to your brain against gravity's resistance. The walls of your veins are thicker in your legs than in your arms, because they have to withstand the higher pressure of a blood column that gravity is constantly trying to pull back down. Even the simple act of standing up triggers an elegant automatic response in your vascular system, a rapid redistribution of blood pressure and volume to prevent you from fainting as gravity pulls blood toward your feet. Every heartbeat, every breath, every postural shift you make is a negotiation with gravity. Remove gravity, and the negotiation ends. And what follows is not freedom. It is confusion. Systemic, progressive, physiological confusion that begins within hours and does not stop. The most immediate effect of microgravity on the human circulatory system is a phenomenon that every astronaut who has ever reached orbit has experienced, usually within the first few hours of arriving. It is called fluid shift, and it is exactly what it sounds like. In the absence of gravity pulling fluid toward the lower body, the blood and other bodily fluids that are normally distributed with a slight bias toward the legs and abdomen begin to redistribute themselves more evenly throughout the body. In practice, this means that fluid moves upward, into the chest, into the neck, into the head. Astronauts describe the sensation as feeling like being perpetually upside down, like the head-rushing fullness you experience when you hang over the edge of a bed, except that it never goes away. The face becomes visibly puffy, the neck veins become distended, nasal passages become congested in a way that feels exactly like the beginning of a head cold, and in the early days of a mission this congestion is essentially permanent. The legs, meanwhile, become thinner, the fluid that normally fills their tissues having migrated northward, giving astronauts what is sometimes informally called bird legs, a puffy torso and comparatively thin lower limbs that look, in photographs, subtly but unmistakably wrong. The body's response to this fluid shift reveals something important about how it interprets the signals it's receiving. The sensors in the large blood vessels near the heart that monitor blood volume detect the increased fluid in the upper body and conclude, incorrectly, that the body is overhydrated. They are not wrong by their own logic. From the perspective of a sensor designed to work in a gravity environment, an elevated fluid level in the chest and head does look like excess volume. So the body responds the way it always responds to what it perceives as excess fluid. It begins excreting it. The kidneys increase urine output. Plasma volume drops. The total volume of blood circulating in the body decreases by as much as 22% within the first few days of spaceflight. This is the body correcting a problem that does not actually exist, reducing a resource it will desperately need, because it is working from instructions written for a world with gravity and applying them to a world without it. The result is a cardiovascular system that arrives in space already well adapted and then systematically undermines its own adaptation based on faulty environmental feedback. But the most consequential and the most troubling effect of fluid shift in microgravity is not what it does to the chest or the legs or the plasma volume. It is what it does to the eyes. The intracranial pressure, the pressure of the cerebrospinal fluid that surrounds the brain and the optic nerves, increases as fluid accumulates in the head. This elevated pressure is transmitted along the optic nerve sheath to the back of the eye, where it pushes against the optic disc, the point where the optic nerve connects to the retina. In a significant proportion of astronauts on long-duration missions, this pressure causes a condition called spaceflight-associated neuroocular syndrome, which NASA researchers have given the acronym SANS. The optic disc swells. The retina can develop folds. The eyeball itself, that precisely shaped optical instrument, changes shape under the sustained pressure, becoming slightly flattened at the back, and as the shape changes, so does vision. Many astronauts returning from long missions need stronger corrective lenses than they did before they left. Some report that their vision did not fully return to its pre-flight baseline even after months back on Earth. In at least some cases, the changes appear to be permanent. Think about what that means for a moment. The eye is a structure of extraordinary precision. The focal length of the lens, the curvature of the cornea, the distance between the lens and the retina, all of it is calibrated to within fractions of a millimeter to produce clear vision. Evolution spent hundreds of millions of years refining that calibration, and a few months of living in microgravity, simply by rerouting the fluid that gravity used to keep in the lower body, can measurably deform that structure. Not through any dramatic trauma, not through any impact or injury or disease, simply through the sustained presence of slightly elevated pressure against the back of the eye, day after day, while the astronaut sleeps and works and exercises and eats and goes about the entirely ordinary business of being alive in an extraordinary place. The eye does not know it is in space. It only knows that something is pushing on it, and it responds the only way it can, by slowly yielding to the pressure, by slowly becoming something slightly different from what it was. The heart, too, changes. In microgravity, the heart does not have to work as hard to pump blood upward against gravity, and like any muscle that is not fully challenged, it begins to decondition. Cardiac muscle mass decreases. The heart becomes slightly smaller and slightly rounder in shape. its output efficiency changes. Astronauts returning from long missions sometimes experience orthostatic intolerance, a condition in which the heart and vascular system, having adapted to a gravity-free environment, struggle to maintain adequate blood pressure when gravity is reintroduced. Some astronauts returning from the International Space Station have had difficulty standing up after landing. Some have fainted. Scott Kelly, who spent 340 consecutive days aboard the station in 2015 and 2016, described the pain of readapting to Earth's gravity as one of the most physically difficult experiences of the mission. His skin, hypersensitized after nearly a year without the constant pressure of clothing and air against it, reportedly hurt to touch. His legs, weakened and fluid depleted, ached under the unfamiliar weight of his own body. He had gone to space a healthy, exceptionally fit human being. He came back a body that had to relearn painfully and slowly how to be on Earth. Your blood knows where it is, and when you take it somewhere it was never meant to go, it tells you. Eventually it tells you in ways that are very hard to ignore. Your skeleton is not a passive structure. I want to start there, because I think most of us carry a mental image of bones as something static, something inert, the rigid scaffolding underneath the living parts of us that simply holds everything in place the way the frame of a building holds up the walls and the roof. But that image is wrong, or at least profoundly incomplete. Your bones are living tissue. They are metabolically active, constantly being broken down and rebuilt in a process that physiologists call remodeling, a continuous negotiation between two types of specialized cells: osteoclasts, which dissolve old or damaged bone tissue, and osteoblasts, which lay down new bone in its place. This process happens throughout your life, and it is regulated by a complex interplay of hormones, nutrition, genetics, and one factor above all others that turns out to be absolutely critical to maintaining bone density and structural integrity. That factor is mechanical load, stress, the physical force of gravity pressing down on your skeleton and the muscles pulling against it with every movement you make. Your bones, it turns out, need to be used. They need to be pushed and pulled and compressed and tensed. Without those forces acting on them continuously, the osteoclasts keep dissolving and the osteoblasts slow down, and the balance shifts, and the bone begins to thin. In space, where gravity is effectively absent, that thinning begins almost immediately and proceeds at a rate that is by any measure alarming. The numbers are stark and worth sitting with. Astronauts on long-duration missions aboard the International Space Station lose bone density at a rate of approximately 1 to 2% per month in the load-bearing regions of the skeleton, primarily the hips, the spine, and the legs, 1 to 2% per month. To put that in context, postmenopausal women on Earth, who experience accelerated bone loss due to hormonal changes and represent one of the highest risk groups for osteoporosis, lose bone density at roughly 1 to 2% per year. Astronauts in microgravity lose that much in a single month. In 6 months aboard the station, an astronaut can lose the equivalent of a decade of age-related bone decline on Earth, compressed into half a year. And while bone density partially recovers after return to Earth, studies of astronauts who have completed long missions suggest that recovery is slow, sometimes incomplete, and that certain structural changes to the bone architecture may persist long after the density numbers have normalized. The skeleton remembers what it went through, and it does not always fully forget. The mechanism behind this loss is elegant in its logic and brutal in its consequences. On Earth, every time you stand, every time you walk, every time you shift your weight from one foot to the other, your skeleton is experiencing compressive loads that signal to the osteoblasts that their work is needed. The bones of your legs and hips are under constant gravitational compression simply by virtue of supporting your body weight, and that compression is interpreted by the bone tissue as a demand to maintain its density and strength. Your muscles, too, contribute. Every time a muscle contracts and pulls against a bone, it creates tensile stress in the bone that further stimulates remodeling and growth. In microgravity, both of these signals disappear simultaneously. Your legs no longer support your weight. Your postural muscles no longer work against gravity to keep you upright. The compressive and tensile loads that your skeleton has received every waking moment of your life on Earth simply stop. And the bone tissue, receiving no signal that its density is required, begins to shed what it no longer needs to maintain. Astronauts aboard the International Space Station exercise for approximately 2 hours every single day specifically to counteract this process. The exercise equipment aboard the station includes a treadmill with a harness system that presses the astronaut against the belt to simulate gravitational load, a stationary bicycle, and a resistance exercise device that uses vacuum cylinders to provide up to 270 kilograms of resistive force. This is not exercise in the recreational sense. It is medical treatment. It is a daily intervention specifically designed to fool the skeleton into behaving as though gravity is present by substituting mechanical load through muscle contraction and impact. And it works, partially. Exercise significantly reduces bone loss rates compared to sedentary microgravity exposure. But it does not eliminate bone loss entirely. Even with 2 hours of vigorous daily exercise, astronauts still lose bone density at rates that would concern any physician treating a patient on Earth. The skeleton is not easily fooled. It knows the difference between real gravity and a treadmill harness in ways that our best engineering has not yet been able to fully bridge. There is a companion process to bone loss in microgravity that is equally significant and equally rapid: muscle atrophy. The relationship between muscle and bone is intimate and reciprocal, each depending on the other for its maintenance and health. In microgravity, the muscles that normally work hardest against gravity, the postural muscles of the back and legs and core, experience a sudden and total reduction in their workload. They are no longer needed to hold the body upright. They are no longer firing hundreds of times per day in the small, constant adjustments that keeping a body balanced and vertical on Earth requires. And muscle tissue, like bone tissue, responds to disuse by reducing itself. Muscle protein is broken down and excreted. Muscle fibers shrink. Strength decreases. Studies have shown that without countermeasures, astronauts can lose up to 20% of their muscle mass in just 5 to 11 days of spaceflight. In longer missions, the losses compound. Astronauts returning from 6-month missions on the International Space Station, even with their rigorous exercise regimens, often require weeks of physical rehabilitation before they can reliably walk without assistance, climb stairs, or perform the ordinary physical tasks of everyday life on Earth. I want you to imagine that for a moment. You leave Earth as a healthy, physically capable human being. You spend 6 months in space doing everything right, exercising daily, eating carefully, taking supplements, following every protocol that decades of space medicine research has developed. You come home, and you cannot reliably walk, not because anything catastrophic happened to you, not because you were injured, but simply because you lived for 6 months in an environment that your skeleton and your muscles were never designed to inhabit. The body is not being dramatic about this. It is not being fragile or weak. It is doing exactly what it evolved to do, conserving resources when those resources are not needed. On Earth, that same adaptive capacity is a feature. The skeleton and muscle tissue of an inactive person thin and weaken because the body is efficiently redirecting energy away from structures that are not being used. In space, what was a feature becomes a liability of the most fundamental kind. The bones remember gravity. They remember it the way a language remembers the grammar of its origin, structurally, invisibly, in the deepest level of their function. And when gravity is gone, they do not adapt gracefully. They simply wait, growing thinner and quieter for the weight of the world to return. We have spent a great deal of time tonight talking about the body, about blood and bone and pressure and oxygen and the precise physiological mechanisms through which the space environment dismantles human biology. And all of that is real, and all of it matters. But there is another dimension to the question of human survival in space that is harder to measure, harder to quantify, and in some ways harder to confront than any of the physical threats we have discussed. It is the dimension of the mind, of psychology, of what happens to human consciousness, human emotion, human identity, when you remove a person from every environmental context that human consciousness evolved inside and place them in a sealed metal cylinder, floating in a darkness so complete and so vast that the word vast does not begin to describe it. The body in space faces threats that can be named and measured and partially mitigated by engineering. The mind in space faces something different, something that engineering can reduce but cannot solve, something that reaches into the deepest architecture of what it means to be a human being and finds the parts of it that were never designed for this. Let me start with isolation, because isolation is the most obvious psychological challenge of spaceflight, and also the one that is most consistently underestimated by people who have not experienced it. Isolation in space is not like isolation on Earth. On Earth, even in the most remote circumstances, there is an outside. There is a world beyond the walls of wherever you are. The Antarctic winter-over crews who spend months at the South Pole, completely cut off from the rest of civilization by weather and distance, are still on the same planet as everyone they have ever loved. They can look at the same sky. They can breathe the same atmosphere. The ground under their feet is connected, however remotely, to the ground under the feet of everyone else. In space, that continuity is severed. The outside the astronaut exists within is not a world. It is the absence of a world, repeated in every direction without limit. The psychological weight of that is something that astronauts consistently describe as difficult to communicate to people who have not seen it firsthand. Not the danger of it, not the fear of it necessarily, simply the sheer, relentless presence of the void, visible through every window, in every direction, always there, always the same, always absolute. The crews aboard the International Space Station live and work in a pressurized volume, roughly equivalent to a 6-bedroom house. This sounds spacious until you consider that they share it with 5 other people, none of whom they chose to live with, all of whom they cannot leave for months at a time. The station's interior is a maze of racks and equipment and cables and modules that, despite being large by spacecraft standards, has more in common with the interior of a submarine than with any living space most people would find comfortable for a week, let alone 6 months. There is no privacy in any meaningful sense. There is no quiet in the earthly sense, because the station's life support systems run continuously and produce a constant background noise of fans and pumps that astronauts describe as inescapable. There is no night and no day in any rhythm the body recognizes, because the station orbits Earth every 90 minutes, cycling through 16 sunrises and 16 sunsets every 24 hours, a light cycle that human circadian biology was never designed to track. Sleep is difficult. Truly restful sleep, the kind that leaves you feeling restored and whole, becomes rare, and the cumulative effect of months of suboptimal sleep, constant noise, artificial light cycles, confined quarters, and inescapable proximity to the same small group of people produces a particular kind of psychological erosion that space medicine researchers have studied carefully and still struggle to fully prevent. The documented psychological effects of long-duration spaceflight are sobering in their breadth and their specificity. Cognitive performance, including working memory, attention, and processing speed, declines measurably in the second half of long missions. Emotional regulation becomes more difficult. Small frustrations that would be easily managed on Earth can become disproportionately charged in the confined, high-stakes environment of a spacecraft. Interpersonal friction within crews is common and well documented, and in at least one case during the early years of the Mir space station program in the 1980s and 1990s, crew conflict became serious enough to affect mission operations. The phenomenon, sometimes called third quarter syndrome, a notable dip in morale and performance that tends to occur roughly 3/4 of the way through a long mission, has been observed consistently enough that it is now planned for in mission scheduling and psychological support protocols. The mind, like the body, does not adapt to the space environment gracefully or completely. It copes, it manages, but it pays a price for coping that accumulates over time in ways that are not always visible until they become impossible to ignore. And then there is the overview effect. I want to spend a moment here because it is something different from the other psychological challenges, something that moves in a different emotional direction entirely. The overview effect is a term coined by the writer Frank White in 1987 to describe a cognitive and emotional shift that many astronauts report experiencing when they first see Earth from space. Not the intellectual knowledge that Earth is a planet in space, which every educated person carries, but the direct, unmediated, visceral experience of seeing it. A small, curved, luminous object hanging in absolute blackness, impossibly beautiful, impossibly fragile looking, with no borders visible and no divisions between the nations and the peoples that from down here seem so urgently and permanently separate. Astronauts who have experienced this shift describe it in remarkably consistent terms across different cultures and different missions and different eras of spaceflight. A sudden, overwhelming sense of the interconnectedness of everything on that small surface, a feeling that the conflicts and divisions that structure life on Earth are revealed, from that altitude, as almost absurdly arbitrary. A love for the planet that feels less like sentiment and more like recognition, as though something the person always knew abstractly has suddenly become undeniable and immediate and real. The overview effect is profound and moving and, in the accounts of those who have experienced it, genuinely life-changing, but it is also, I think, a window into something psychologically complex about the space experience. Because the same altitude that produces that overwhelming sense of love and connection also produces in many astronauts a parallel and quieter experience of existential dread. The smallness of Earth from orbit is beautiful. It is also terrifying. The blackness surrounding it is not a backdrop. It is the reality, and Earth is the exception, and the exception is very, very small. Some astronauts have described lying in their sleeping bags aboard the station, floating in the darkness with no sense of up or down, looking out the window at the void and feeling the full weight of where they were in a way that went beyond intellectual comprehension into something more physical, more animal. A recognition, below the level of thought, that they were very far from home, that home was very small, and that between them and it there was nothing. No ground, no air, no sound. Nothing but the dark and the distance and the absolute indifference of space to the fact that they were there at all. The mind, in the end, was not built for that view, and knowing that changes something in you, even when you are safely back on Earth, looking up at the stars from the bottom of the bubble, wondering what it felt like to be outside it. Everything we have talked about tonight, every threat, every cascade of physiological failure, every silent and merciless process through which the space environment dismantles human biology, has a single engineering answer. One object stands between all of that and the person inside it. One object takes the vacuum and the radiation and the temperature extremes and the oxygen deprivation and says, "Not today, not this person, not while I am here." That object is the spacesuit, and I want to spend some time with it tonight, not just because it is one of the most sophisticated pieces of engineering ever created by human beings, but because understanding what the spacesuit does, layer by layer and system by system, is perhaps the clearest possible way to understand what space is actually like. Every function the suit performs is a direct answer to a specific threat. Every layer it contains exists because without that layer, something specific and terrible would happen to the body inside it. The spacesuit is not clothing. It is not protective gear in the way a helmet or a life jacket is protective gear. The spacesuit is a miniature planet, a portable Earth, a wearable bubble of the exact conditions that human biology requires, carried into a place where those conditions are catastrophically, completely absent. The suit used by NASA astronauts for extravehicular activity, spacewalks outside the International Space Station, is called the Extravehicular Mobility Unit, or EMU. It has been in use, with continuous upgrades and modifications since the early years of the Space Shuttle program in the 1980s. It is not a single garment. It is a system of systems, a collection of interlocking components that together replicate inside a volume roughly the size and shape of a human body, the life-sustaining functions of an entire planetary atmosphere. The suit weighs approximately 130 kilograms on Earth, though in the microgravity of orbit that weight is irrelevant. It takes approximately 45 minutes to put on correctly, and doing so requires assistance from another crew member. It is pressurized to about 30% of standard sea-level atmospheric pressure, using pure oxygen rather than the nitrogen-oxygen mixture of Earth's air, which means astronauts must breathe pure oxygen for several hours before a spacewalk to purge the nitrogen from their blood and prevent decompression sickness when the pressure drops. Putting on a spacesuit is not a casual act. It is a medical procedure. The outermost layer of the EMU is a shell of orthofabric, a material woven from a blend of Gore-Tex, Kevlar and Nomex, the same material used in firefighting gear and bulletproof vest construction. This layer serves as the first line of defense against micrometeorites and orbital debris, tiny particles of rock and human-made material that travel through low Earth orbit at speeds of up to 28,000 kilometers per hour. A particle the size of a grain of sand moving at that speed carries the kinetic energy of a bowling ball dropped from a considerable height. The outer fabric layer is not impervious to large debris, nothing is, but it absorbs and dissipates the energy of the smaller impacts that are the constant background condition of working in orbit. Beneath that outer shell are multiple layers of aluminized mylar. thin reflective films that serve as thermal insulation, alternating with layers of Dacron spacer fabric. These thermal layers manage the extreme temperature differential between the sunlit and shadowed sides of the suit, preventing both overheating in direct sunlight and catastrophic heat loss in shadow. There are 14 layers in total between the outermost shell and the innermost pressure garment. 14 layers, each one performing a specific function, each one the answer to a specific way the space environment would otherwise reach in and begin its work. The innermost layer that matters most from a survival standpoint is the pressure bladder, a sealed garment of urethane-coated nylon that is inflated with pure oxygen to maintain the pressure the body requires for its fluids to remain in solution and its lungs to function. This is the layer that does the work that the atmosphere does on Earth, the layer that pushes back. Without it, ebulism begins in seconds. With it, the body inside the suit exists, as far as its pressure-dependent systems are concerned, in something approximating a habitable environment. The oxygen inside the suit is continuously circulated, with carbon dioxide removed by a lithium hydroxide canister and moisture extracted to prevent the visor from fogging and the astronaut from breathing increasingly humid carbon dioxide-rich air. The system has enough consumables, oxygen, battery power, and carbon dioxide absorption capacity to sustain an astronaut for approximately 8 hours during a normal spacewalk with a reserve margin for emergencies. 8 hours. That is the window the suit creates between a human being and the void. 8 hours of borrowed Earth, strapped to your body, holding the universe at arm's length. The suit also contains a liquid cooling and ventilation garment worn directly against the skin, a network of thin tubes through which chilled water is continuously circulated to remove the body heat generated by the physical exertion of spacewalk work. This is necessary because in a pressurized suit with no convective cooling from moving air, body heat has nowhere to go. Without active cooling, an astronaut performing physical labor in a spacesuit would rapidly overheat to dangerous and then lethal temperatures. The cooling system is controlled by the astronaut through a simple dial that adjusts the water temperature, and getting the setting right is a constant minor task during spacewalks because the thermal load on the body changes constantly as the astronaut moves between sunlight and shadow, exerts different levels of physical effort, and manages the insulating effect of the suit itself. The suit communicates with the astronaut through a display and control module on the chest, which shows oxygen pressure, suit pressure, battery life, carbon dioxide levels, and cooling water temperature. In a very real sense, the astronaut is flying the suit the way a pilot flies an aircraft, monitoring systems and making continuous small adjustments to maintain the environment inside the suit within the narrow range that keeps the person inside alive. And here is what I want you to take from all of this, as you lie quietly in the dark and let these ideas settle into you. The spacesuit is an answer, a brilliant, painstaking, enormously expensive and technically demanding answer to the question of how to keep a human being alive in a place that is trying, with the full and indifferent force of physics, to end them. And the fact that the answer is this complicated, this heavy, this layered, this fragile in its dependence on batteries and oxygen canisters and pressure seals and cooling pumps, tells you something profound about the question. The question is not a small one. The question is not a problem with a simple solution that engineers just haven't gotten around to finding yet. The question is fundamental. Space requires, from any human presence within it, a complete and continuous replication of Earth. Not an approximation, not a simplification. Earth. The pressure, the oxygen, the temperature regulation, the radiation shielding, the psychological support systems, all of it, carried along at enormous cost and complexity for every moment a human being is out there. The spacesuit does not conquer space. It creates a tiny, temporary, magnificently engineered exception to space, and the moment that exception fails, in any one of a dozen ways, the universe quietly, efficiently resumes what it was doing before we interrupted it, which is exactly nothing, which is exactly everything we are not. On the 2nd of November in the year 2000, 2 human beings climbed aboard a Soyuz spacecraft, rode a column of controlled fire into low Earth orbit, docked with a partially assembled space station, opened a hatch, and floated inside. Their names were Bill Shepard and Yuri Gidzenko, along with flight engineer Sergei Krikalev, and they were the first crew of what would become the longest continuously inhabited human outpost beyond Earth. More than 25 years later, that outpost is still occupied. Not by the same people, obviously, but by someone, always by someone, a rotating cast of human beings from more than a dozen nations who live and work in low Earth orbit in shifts, handing the station off to incoming crews the way relay runners pass a baton, ensuring that the thread of continuous human presence in space is never broken. The International Space Station is, by almost any measure, the most complex and expensive structure ever built by human beings. It cost approximately $150 billion to construct and operate. It involved the contributions of 15 nations and 5 space agencies. It took more than 40 assembly flights over more than a decade to put together in orbit, piece by piece, like the world's most expensive and dangerous puzzle, assembled in a vacuum 400 kilometers above the surface of the Earth. It is magnificent. It is audacious. And it is, when you look at it clearly and honestly, surviving by the thinnest thread imaginable. The station orbits Earth at an average altitude of approximately 408 kilometers, traveling at roughly 28,000 kilometers per hour, completing one full orbit every 90 minutes. At that speed, the station is essentially in a continuous state of controlled falling, moving fast enough horizontally that as it falls toward Earth, Earth's surface curves away beneath it at the same rate, creating the perpetual near miss that we call orbit. The station must be periodically reboosted to maintain this altitude, because even at 400 kilometers the atmosphere has not entirely disappeared. There is a thin, tenuous exosphere of gas molecules that creates a tiny but real drag on the station, gradually lowering its orbit over time. Without periodic boosts from visiting spacecraft or the station's own thrusters, the International Space Station would gradually slow, descend, and eventually re-enter the atmosphere and burn up. The station is not safely parked in space. It is continuously, actively staying there, requiring fuel and maintenance and operational attention every single day to remain where it is. Inside the station, the life support systems that keep 6 human beings alive operate with a complexity and a fragility that most people who see the beautiful photographs of the gleaming exterior never fully appreciate. The atmosphere inside the station is maintained at sea level pressure and a nitrogen-oxygen composition similar to Earth's air, scrubbed continuously of carbon dioxide by chemical absorption systems and of trace contaminants by activated charcoal filters and catalytic oxidizers. The water supply is recycled almost entirely from the crew's own waste, a fact that astronauts learn to make peace with fairly quickly. Urine is collected, processed through a urine processor assembly that uses vacuum distillation and chemical treatment to extract pure water, combined with condensed humidity recovered from the cabin air and then further purified through a water processor assembly to produce drinking water that is, by chemical analysis, cleaner than most municipal tap water on Earth. The carbon dioxide removed from the cabin air is partly used to produce oxygen through a process called the Sabatier reaction, which combines carbon dioxide with hydrogen to produce water and methane, with the water then electrolyzed to extract oxygen. The system is elegant and closed and efficient. It is also continuously requiring maintenance, producing unexpected failures, and demanding the attention of crew members who are already fully occupied with their scientific and operational duties. Here is something that rarely makes it into the public narrative about the space station, something that the glossy mission photographs and the upbeat press releases tend to smooth over. The station is old. It is aging. The first modules launched in 1998 and have now been in the radiation-soaked, thermally cycling, micrometeorite-peppered environment of low Earth orbit for more than a quarter of a century. Metal fatigues, seals degrade, insulation breaks down. The station has experienced hundreds of micrometeorite and debris impacts over its operational life, most of them too small to cause structural damage, but each one a reminder of the constant bombardment that everything in low Earth orbit endures. In 2021, a small air leak was traced to a crack in a Russian module that had been present and slowly growing for years. The crew managed it, as they manage most things, with a combination of technical skill, improvised solutions, and the particular kind of calm that comes from training extensively for exactly these scenarios. But the leak was there, the crack was there, and the air on the other side of that crack was the void. A micrometeorite the size of a paint fleck travelling at orbital velocity hits the station's exterior with the energy of a rifle bullet. The station's outermost hull layers are designed to handle particles up to about 1 centimetre in diameter through a system called Whipple shielding. an outer bumper layer that vaporizes small impactors, with the resulting cloud of debris then dispersed by a gap before reaching the inner pressure wall. It is ingenious. It works well for the size of objects it was designed to handle. But for larger objects, tracked pieces of orbital debris of which there are now more than 23,000 in low Earth orbit above 10 centimeters in size, the only option is to move the station. When radar tracking identifies a conjunction, a close approach between the station and a tracked debris object, mission controllers calculate the probability of impact and, if it exceeds certain thresholds, command the station to perform a debris avoidance maneuver, firing thrusters to nudge the orbit slightly and change the geometry of the encounter. The station has performed dozens of these maneuvers over its lifetime, and on occasions when the warning came too late for a maneuver, the crew is sheltered in the docked Soyuz capsules, their emergency return vehicles, ready to undock and deorbit if the station were catastrophically struck. The crew, in those moments, sat in their emergency lifeboats and waited to find out whether the station they lived in was about to cease to exist. That is not a metaphor. That is a Tuesday. I tell you all of this not to diminish the extraordinary achievement that the International Space Station represents, because the achievement is real, and it is extraordinary, and it deserves every word of admiration it has ever received. I tell you this because the station is the best answer humanity has yet produced to the question of how to keep human beings alive in space, and even this best answer is a structure that leaks, that ages, that requires constant repair, that shelters its inhabitants behind walls that a paint fleck can threaten, that recycles their urine for drinking water, that generates its oxygen through chemistry conducted in a metal box 400 kilometers above everything that has ever kept a human being alive. The station is heroic precisely because it is so fragile. It is a monument to what human ingenuity can accomplish, not by conquering the space environment, but by negotiating with it, day by day, system by system, repair by repair for as long as the thread holds. And the thread holds. It has held for more than 2 decades, but it is thin. It has always been thin. And out there beyond the walls, 400 kilometers below your feet if you were standing inside it, the Earth turns blue and impossible and very, very far away. Mars has captured the human imagination for as long as we have been able to see it. That small, reddish point of light in the night sky, distinct and slightly warm-coloured against the cold white of the stars around it, has carried the weight of our dreams about other worlds for centuries. The ancient Romans named it after their god of war. The ancient Egyptians called it Her-Desha, the Red One. Every civilization that looked up and noticed that wandering point of light gave it significance, gave it meaning, wrote it into their mythology and their cosmology as something apart from the ordinary stars. And in the 20th century, when we finally got close enough to see it clearly, when we sent spacecraft to photograph its surface and land on its rust-coloured plains and drill into its ancient rock, it became something even more charged than a mythological object. It became a destination, a goal, the next step, the place where humanity would go after the moon, the first true outpost of our species beyond the Earth-Moon system, the beginning of something that in our most expansive and hopeful moments we call the multiplanetary future. The dream of Mars is one of the most powerful and enduring dreams our civilization has ever produced, and the body, the ordinary blood and bone evolved for Earth human body, is profoundly, perhaps fatally, unsuited to make the journey. The distance to Mars is not fixed. Because both Earth and Mars are moving in elliptical orbits around the Sun at different speeds, the distance between them varies enormously over time, from about 54.6 million kilometers at closest approach, which happens roughly every 2 years, to over 400 million kilometers when the 2 planets are on opposite sides of the Sun. Space mission planners use specific launch windows when the geometry of the 2 orbits allows the most fuel-efficient trajectory, a curved path called a Hohmann transfer orbit that arcs through the inner solar system and meets Mars at the right point in its orbit. Even on this optimal trajectory, a one-way trip to Mars takes between 6 and 9 months, depending on the specific launch window. And during every single one of those months, the crew of that spacecraft would be exposed to the interplanetary radiation environment. No magnetosphere, no atmosphere, no protection beyond the thin metal walls of the spacecraft and whatever additional shielding mission designers can afford to include without making the vehicle too heavy to launch. The galactic cosmic ray dose during a 6-month Mars transit, based on measurements taken by the Curiosity rover's radiation assessment detector during its own transit to Mars in 2011 and 2012, is approximately 300 millisieverts. To put that in context, the career radiation exposure limit set by NASA for its astronauts is 600 millisieverts, a limit designed to keep the excess lifetime cancer risk below 3%. A single round trip to Mars, transit only, not counting the time on the surface, would consume essentially the entire career radiation budget of an astronaut in one mission, and that calculation assumes no major solar particle events during the journey, which is far from guaranteed. But radiation is not the only thing the journey does to the crew. Remember everything we discussed about the physical effects of microgravity. The fluid shift, the cardiovascular deconditioning, the bone density loss, the muscle atrophy. All of those processes would be running continuously for the entire 6 to 9 month duration of the transit. Astronauts on the International Space Station, as we discussed, already show significant bone and muscle loss after 6 months despite rigorous daily exercise. A Mars transit crew would face the same degradation over the same time frame, arriving at their destination already weakened, already deconditioned, already carrying the accumulated physiological burden of months in microgravity. And Mars, unlike the space station, is not a place where you can simply float and recover. Mars has gravity, roughly 38% of Earth's gravitational pull. The surface must be walked on, equipment must be carried, vehicles must be operated. The work of establishing and maintaining a surface presence on another planet requires physical capability, and the crew would arrive having just spent 6 to 9 months in conditions specifically designed by the laws of physics to erode exactly that capability. They might, in the most demanding scenarios, be too weakened to perform the work the mission requires of them from the moment they set foot on the surface. The psychological dimension of a Mars transit adds yet another layer of complexity to an already daunting picture. We discussed the psychological challenges of long-duration spaceflight in the context of the International Space Station, where crews are, despite everything, only 400 kilometers from Earth. Communication with the ground is essentially instantaneous. A medical emergency can, in theory, result in an emergency return to Earth within hours via a Soyuz capsule. The psychological safety net of proximity, however distant it might feel emotionally, is real. On a Mars transit, that net does not exist. At Mars, the communication delay due to the speed of light ranges from 3 to 22 minutes each way, meaning a conversation with Earth takes a minimum of 6 minutes round trip, and potentially 44 minutes round trip when the planets are far apart. Real-time conversation is impossible. Medical emergencies cannot be managed in real time with ground support. Decisions must be made by the crew autonomously, with whatever medical knowledge and equipment they have aboard, knowing that any help from Earth is a one-way radio signal that will take anywhere from 3 to 22 minutes to arrive. The psychological weight of that isolation, that true and total isolation, is something that no current analog environment on Earth fully replicates, and something that researchers in space medicine are genuinely uncertain about how to prepare crews for. There is also the question of what happens when something goes wrong. And in space, on a mission of this complexity and duration, something will go wrong. It always does. The history of spaceflight is the history of carefully engineered systems failing in unexpected ways at inopportune moments, and crews improvising solutions under pressure with whatever resources they have available. On the International Space Station, a major system failure can often be managed with replacement parts delivered on the next supply mission, which arrives every few months. On a Mars transit, there are no supply missions. There is no next delivery. Whatever breaks must be fixed with what is aboard, or worked around, or lived without. Every component of every critical system must either have a spare or have a workaround, and the spacecraft must carry all of those spares and all of those workaround components for the entire duration of the mission. The logistical demands of this self-sufficiency requirement are enormous and add mass and complexity that push against the fundamental constraints of what can actually be launched from Earth's surface. None of this means that a human mission to Mars is impossible. I want to be clear about that. Humans are extraordinarily adaptable. Engineering is extraordinarily capable of solving problems when given sufficient time and resources and motivation. The challenges of a Mars mission are real and they are serious. But they are the kind of challenges that serious, well-funded, intelligently directed engineering programs can make meaningful progress on. Better radiation shielding, artificial gravity through rotation, improved exercise countermeasures, faster transit trajectories, closed-loop life support systems, pharmaceutical countermeasures for bone loss, psychological support protocols. Each of these is an active area of research, and each of them represents a genuine pathway toward making the journey survivable in a deeper and more complete sense than it currently is. But the gap between where we are and where we need to be is not a small one, and the gap is not primarily a gap in technology or funding or political will, though all of those things matter. The gap is in the body itself, the body that evolution built for one very specific world, and that carries, in every cell and every bone and every carefully regulated system, the assumption that it will never be asked to leave it. Mars is the dream. The body is the constraint. And the distance between them is measured not just in millions of kilometers, but in billions of years of evolution that never once imagined we would be audacious enough to try. 3.8 billion years. That is the number I want you to hold in your mind as we move into this part of the story. 3.8 billion years is the approximate age of life on Earth, the span of time between the first self-replicating molecules that flickered into existence in the ancient oceans of a young planet, and the particular arrangement of cells and systems and consciousness that is you, lying here in the dark, breathing slowly, listening to the universe being described. 3.8 billion years of trial and error. 3.8 billion years of mutation and selection and extinction and adaptation, generation by generation, environment by environment, crisis by crisis. Every feature of your body, from the curve of your spine to the chemistry of your tears to the precise electrical threshold at which your neurons fire, is the outcome of that process, not designed, not planned, but refined, with a patience and a thoroughness that no human engineering program has ever come close to matching, by the single most powerful optimization process the universe has yet produced. Evolution does not have a goal. It does not have a direction. It has only a filter. What works, survives. What does not, disappears. And after 3.8 billion years of filtering, what is left is extraordinary. What is left is you. And what is left is entirely, precisely, and without a single exception, optimized for one specific place. That place is Earth, not space, not Mars, not the interstellar medium or the surface of the Moon, or the orbital environment of low Earth orbit. Earth. One planet, one gravitational field of 9.8 meters per second squared, one atmospheric pressure of 101,000 pascals at sea level, one oxygen concentration of 21%, one magnetic field deflecting cosmic radiation, one temperature range within which liquid water exists and proteins fold correctly, and enzymes function, and cell membranes maintain their integrity, one circadian rhythm set by one star at one specific distance, cycling through light and dark on a 24-hour schedule that your body has internalized so deeply that disrupting it for even a few days produces measurable cognitive and physiological impairment. Evolution did not prepare you for anywhere else. It could not have. The process works by selecting for survival in the environment that actually exists, not the environments that might theoretically exist elsewhere. And for 3.8 billion years, the environment that actually existed, for every ancestor of yours in an unbroken chain stretching back to the first cell, was this one. This specific, improbable, extraordinarily well-suited to life planet that you have spent your entire existence sitting on without once needing to think about how lucky that is. Consider what this means at the level of individual biological systems, because I think the depth of the optimization becomes most visible when you look at the specifics. Your cardiovascular system is not a generic pump. It is a pump designed for Earth's gravity, with pressure gradients calibrated to the specific challenge of moving blood upward against a gravitational field of exactly 9.8 meters per second squared. Change the gravitational field, and the calibration is wrong. Your immune system is not a generic defense mechanism. It is a system shaped by 3.8 billion years of exposure to the specific pathogens, parasites, and environmental stresses of Earth's surface, and it makes assumptions about the chemical environment it operates in that are based entirely on Earth's chemistry. Your circadian clock is not a generic timer. It is synchronized to the 24-hour rotation of one specific planet around one specific star, and it runs so deeply in your biology that it is encoded in the gene expression patterns of nearly every cell in your body. Your vestibular system, the inner ear structures that tell you which way is up, is calibrated to one specific gravitational reference. In microgravity, it receives signals it was never designed to interpret, producing the spatial disorientation and nausea that affects the majority of astronauts in their first days in orbit. The system is not broken. It is working exactly as it was designed to work. It simply was not designed for this. Here is the thing most people do not realize when they think about the human body in space. The conversation is usually framed as a problem to be solved. The body is not suited for space. Therefore, we need to develop technology and medicine to make it suited for space. And that framing is not wrong, exactly. It is just incomplete, because it treats the body's unsuitability for space as a deficiency, as something lacking, as a gap to be filled. But the body's unsuitability for space is not a deficiency. It is the signature of an optimization so thorough and so complete that it has left no excess capacity for environments that never existed in the selective history of life on Earth. A fish is not deficient because it cannot breathe air. It is perfectly optimized for water. The deficiency framing only makes sense if you assume that the fish should have been designed to breathe air, which it should not have been, because it never needed to. You're not deficient because you cannot survive in space. You're perfectly optimized for Earth. The question is not what is wrong with you. The question is what you are being asked to do that 3.8 billion years of evolution never once asked of any of your ancestors. And that question, when you really sit with it, opens into something philosophically vertiginous. Because what we are asking when we ask human beings to go to space is not a modest request. We are not asking them to go somewhere slightly outside their comfort zone, somewhere that requires a bit of adaptation and acclimatization. We are asking them to leave the only environment that life has ever existed in, as far as we know, and enter an environment that is the precise negation of everything that life requires. We are asking evolution's masterpiece to operate in the one context that evolution never imagined, never prepared for, and never had any reason to. And we are asking it to do this not by changing the biology, not by redesigning the organism, but by wrapping the organism in engineering and hoping the engineering holds. The spacesuit, the spacecraft, the life support systems, the radiation shielding, the exercise protocols, all of it is not adaptation, it is accommodation. It is the engineering equivalent of carrying your environment with you, because your environment is the only one that will keep you alive. There is something both humbling and magnificent about this, and I want you to feel both of those things as we move toward the end of tonight's journey. The humbling part is obvious. We are not cosmic beings. We are not naturally suited to the cosmos. We are Earth beings, through and through, in every cell and every system, and the universe is under no obligation to accommodate us simply because we find it beautiful and want to explore it. The magnificent part is perhaps less obvious but equally true. We are the only species that has ever looked at an environment completely incompatible with its biology and said, we are going anyway. We are the only product of evolution that has ever turned its curiosity on the conditions of its own existence, understood those conditions clearly enough to replicate them artificially, and then carried that artificial bubble of home into the hostile dark and survived there, however briefly, however precariously, however at enormous cost and effort and risk. Evolution never prepared us for space, and we went anyway. That gap between what we were built for and what we reached for is perhaps the most human thing about us. It is the gap where all of our science and all of our engineering and all of our poetry lives. It is the gap we have been crossing one fragile mission at a time for less than a single human lifetime. And it is, I think, the most extraordinary thing our species has ever done. There is a question that sits underneath everything we have discussed tonight, a question that all of the biology and the physics and the engineering history has been building toward, without quite stating directly. It is not a technical question, though it has technical dimensions. It is not a political question, though it has political ones. It is older and stranger and more fundamental than either of those things. The question is this: is space a place we are passing through, or a place we are moving toward? Is the cosmos something we will always visit as temporary, fragile, enormously expensive guests, carrying our little bubble of Earth wherever we go, and counting the days until we can return to the only environment that will have us? Or is there a version of this story in which we genuinely belong out there, in which the gap between human biology and the space environment is not a permanent condition, but a transitional one, a phase in a longer arc that ends somewhere we cannot yet clearly see? I do not know the answer to that question. No one does. But I think it is worth spending some time with the possibilities, not because they are certain, but because they are real, and because the shape of what might be possible tells us something true about where we stand right now and how far we have yet to go. The most immediately practical pathway toward reducing the gap between human biology and the space environment does not involve changing the biology at all. It involves improving the environment that the biology is carried into. Better radiation shielding is perhaps the most urgent engineering priority for deep space human exploration. Current shielding technology, based primarily on aluminum and polyethylene, is effective against solar particle events, but largely ineffective against the highest energy galactic cosmic rays. Researchers are exploring materials with higher hydrogen content, since hydrogen atoms are particularly effective at breaking up cosmic ray particles through a process called spallation. Water walls, in which the structural walls of a spacecraft are filled with water that serves simultaneously as shielding, thermal regulation, and emergency drinking supply, have been proposed and studied. Active magnetic shielding, essentially a miniature version of Earth's own magnetic field generated by superconducting electromagnets surrounding the spacecraft, has been theorized for decades and is now the subject of serious engineering research. None of these solutions are ready, none of them are cheap, but none of them are physically impossible, and progress on each of them is real and ongoing. Artificial gravity is another engineering pathway that would address multiple biological problems simultaneously. If a spacecraft could be designed to rotate, the centrifugal force experienced by the crew would simulate gravity, preventing the fluid shift, the bone loss, the muscle atrophy, and the cardiovascular deconditioning that make long-duration spaceflight so physiologically costly. The mathematics of artificial gravity are straightforward. A rotating structure of sufficient size and rotation rate produces a centripetal acceleration that is indistinguishable, from the perspective of the human vestibular system and skeleton, from real gravitational pull. The engineering challenges are significant but not insurmountable. A rotating habitat large enough to avoid the nausea-inducing effects of differential rotation across the body would need to be quite large, and launching large structures into space is expensive. But conceptual designs for rotating spacecraft have existed since the 1960s, and several serious proposals for rotating Mars transit vehicles have been developed in the past decade. Artificial gravity may be the single most transformative technology available for making long-duration human spaceflight biologically sustainable, and the fact that we have not yet built a rotating spacecraft for human use is a matter of cost and priority, not of physical impossibility. But beyond engineering, there is another pathway that raises deeper and more complex questions. What if the solution is not to bring Earth to the human body, but to change the human body itself? The tools of modern genetics and synthetic biology are advancing at a pace that would have seemed like science fiction 20 years ago. CRISPR gene editing allows researchers to make precise, targeted modifications to DNA sequences with a speed and accuracy that were not possible before its development in the early 2010s. Researchers have already identified genes associated with radiation resistance in organisms like the bacterium Deinococcus radiodurans, which can survive radiation doses thousands of times higher than those that would kill a human being. They have identified the genetic basis of the extraordinary bone density maintenance seen in hibernating bears, which do not experience bone loss during months of inactivity the way humans do. They have studied the genetics of organisms that can survive vacuum exposure, extreme temperature ranges, and other conditions that human biology cannot approach. The question of whether those genetic traits could, in principle, be introduced into human biology is no longer purely hypothetical. It is a question that genetics researchers are beginning to ask seriously, even if the answers remain far in the future and the ethical dimensions are profound. Hibernation research represents a different but equally fascinating approach to the problem of long-duration spaceflight. Several species of mammals hibernate successfully, dramatically reducing their metabolic rate, body temperature, and oxygen consumption for extended periods, and then recovering fully with no apparent long-term damage. If human beings could be placed in a controlled state of metabolic suppression for the duration of a Mars transit, the physiological challenges of the journey would be dramatically reduced. Less muscle and bone loss due to reduced metabolic activity, less psychological strain from prolonged confinement, reduced food and water requirements, and potentially reduced radiation damage to actively dividing cells. NASA has funded research into torpor-inducing technologies for spaceflight applications, and while true human hibernation remains far beyond current capability, the underlying biology of mammalian torpor is being studied with increasing sophistication. The bears know something we do not yet know, and we are trying to learn it. And then there is the most radical possibility of all, the one that moves furthest from the human body as we currently know it, and into territory that blurs the boundary between biology and technology. Some researchers and philosophers of technology argue that the ultimate solution to the incompatibility between human biology and the space environment is not to modify the biology or improve the engineering, but to move beyond the biology entirely. Whole brain emulation, the theoretical transfer of a human mind into a digital substrate that does not require oxygen or pressure or a specific temperature range, is sometimes proposed as the end state of a trajectory that begins with where we are now and passes through increasingly radical forms of human enhancement. A digital mind could theoretically inhabit a robotic body specifically engineered for the space environment, or no body at all, transmitted as information at the speed of light across interstellar distances in ways that biological organisms could never survive. I am not telling you this is coming. I am not telling you it is possible. I am telling you it is being seriously discussed by serious people, because the gap between what the human body can survive and what space requires of it is wide enough that some researchers have concluded that bridging it with biology alone may not be the right frame for the question. But here is where I land tonight, in the quiet at the end of all of this. I think we will go. I think we will keep going further, and that over time the going will become less impossibly costly and more sustainable, through better engineering and better medicine, and perhaps, eventually, through changes to the biology itself that we cannot yet fully envision. I think the question of whether we belong out there will eventually be answered not by the universe, but by us, by the particular and extraordinary stubbornness of a species that has never once looked at an environment it could not survive in and decided to stay home. We belong wherever we decide to belong. That has always been the human answer to the cosmos. And standing here at the edge of what we currently know, looking out at the distances and the darkness and the radiation and the cold, I find that answer more moving, not less, for knowing how hard the journey actually is. I want to tell you something that I have been holding back for the entirety of tonight, saving for this moment, for the quiet at the end of everything we have covered, when you are still and the dark is full and the universe feels close in the way it only does in the small hours before dawn. It is not a new idea. Scientists have known it for decades, and perhaps you have heard it before in some form. But knowing something and truly feeling its weight are two different experiences, and tonight, after everything we have talked about, I think you are ready to feel it in a way that might be different from any time you have encountered it before. Here it is. The atoms in your body were not made on Earth. They were not made in the solar system. The hydrogen atoms in the water in your cells are as old as the universe itself, formed in the first few minutes after the Big Bang, 13.8 billion years ago. The heavier elements, the carbon in your DNA, the oxygen in your blood, the calcium in the bones that space would slowly dissolve, the iron at the centre of the hemoglobin molecules that carry the oxygen that space would steal away from you, all of those were forged inside stars, inside the nuclear furnaces of massive stars that burned for millions of years and then died in catastrophic explosions called supernovae, scattering their contents across the galaxy in clouds of gas and dust that eventually condensed, over millions more years, into new stars and new planets, into this star, into this planet, into you. You are not on Earth looking up at the stars. You're made of stars looking up at where you came from. And here is the paradox that I find most beautiful and most terrifying about that fact, and the reason I have saved it for this moment. The stars that made you could not survive in space any more than you can. The nuclear fusion reactions at the cores of stars require pressures and temperatures that exist nowhere in the open space between stars. The interstellar medium, the thin gas and dust that fills the galaxy between solar systems, is so cold and so diffuse that chemistry barely happens there. Life, as far as we know, requires a planet. It requires the specific conditions that only a planet can provide. a stable gravitational field, a moderate temperature range, liquid water, an atmosphere, protection from radiation. The atoms that make up your body travelled through billions of years of cosmic history, from the cores of dying stars to drifting nebulae, to the accretion disk of a forming solar system, to the crust of a young planet, to the ocean where life first emerged, and through every form life took on its way to becoming you. And all of that journey was a journey toward exactly the kind of environment that we have spent tonight describing as the one environment your body requires. The universe spent 13.8 billion years making you out of star stuff, and the star stuff, it turns out, needs a very specific address to function. I have thought about this paradox many times, and I find that it does not resolve into something simple. It does not reduce to either tragedy or triumph. It sits in a more complicated place, a place that feels to me like the truest emotional register for thinking about what it means to be a human being in a universe like this one. The tragedy reading is obvious. We are made of the cosmos and yet excluded from it. We carry the universe in our atoms and cannot survive in the universe that those atoms came from. Space would kill us in minutes. The distances between stars are so vast that even if we solved every biological challenge, even if we built the perfect spacecraft with the perfect shielding and the perfect life support and the perfect artificial gravity, the nearest star system is still 4.2 light-years away, and travelling there at any speed currently imaginable would take tens of thousands of years. The cosmos is in us, and we are locked out of it by the very conditions that make us possible. If that is not a kind of magnificent, heartbreaking irony, I do not know what is. But there is another reading, and it is the one I want to leave you with tonight. We are the universe noticing itself. That phrase has been said before, and it risks becoming a cliché through repetition, but I want you to hear it tonight in the specific context of everything we have talked about. The carbon in your body was inside a star. The oxygen in your lungs was scattered across the galaxy in a supernova explosion. The calcium in your bones was drifting through interstellar space for millions of years before it became part of the Earth and eventually part of you. And now, in you, in the arrangement of atoms that makes you conscious and curious and alive, that material has developed the ability to think about where it came from, to build telescopes and point them at the edges of the observable universe and see the light of the first galaxies, to calculate the temperature of the cosmic microwave background to 4 decimal places, to understand with genuine scientific precision the nuclear reactions that forged the atoms in our bodies inside stars that died before our sun existed. The universe has, in us, produced something that can look back at the universe and comprehend it. That is not nothing. That is, in fact, the most extraordinary thing I know. And the fact that we cannot survive out there, the fact that space would take us apart in seconds, and that the distances are so vast and the conditions so hostile that our presence in the cosmos will always be local and fragile and enormously costly, does not diminish that. If anything, it deepens it. Because what it means is that consciousness, this particular form of the universe knowing itself, is a planetary phenomenon. It requires a bubble. It requires the thin coat of paint of an atmosphere and the invisible shield of a magnetic field and the steady warmth of a star at just the right distance and the liquid water and the atmospheric pressure and all of the other conditions that we have spent tonight cataloguing as the things that space removes. Take away the bubble, and in seconds the process that produces awareness is interrupted, which means that awareness, wherever it exists in the universe, is necessarily local, necessarily precious, necessarily rare in the sense that it requires exactly the right conditions to persist at all. You are not the universe in general. You are the universe in one very specific, very improbable, very temporary place. And that place, this planet, this atmosphere, this moment, is the only address consciousness has ever been confirmed to inhabit. Thanks for staying with me through all of this tonight. We have covered a long distance together, from the thin bubble of the atmosphere to the vacuum and the cold, and the radiation, and the bone loss and the isolation, and the philosophical paradox at the centre of all of it. I hope that somewhere in all of that, you found not just information but something that felt, even quietly, like wonder, like the particular kind of wonder that comes from understanding something clearly and finding that the clarity makes it more beautiful, not less. If tonight moved something in you, if it made you want to explore more, I would love it if you would like the video or subscribe to the channel. It is a small thing, but it helps us keep making these journeys together, and there are so many more places I want to take you. For now, though, let that be enough. Let the atoms in your body be enough. Let the improbable fact of your existence on this particular planet at this particular moment in cosmic history be enough. The next time you step outside at night and look up at the stars, I hope you see them a little differently, not as decoration, not as background, but as the place you came from, shining down at the thing they made, across distances that neither of you can cross, in a conversation that has been going on for 13.8 billion years and will continue long after both of us are gone. Sleep well tonight. You're made of stars, and the stars in you are finally briefly awake. Good night.